Welcome back. Let's dig into the data a little further now with some measures of confidence and hypothesis testing. The section will be a little heavy on theory, but I promise whatever you are able to retain will benefit you in your work. The goal of this section is for us to be able to assess the quality of statistics presented to us and understand a little bit about how they are derived. First off, statistics matter. Applying a tried and true statistical analysis method grants you the power of mathematical geniuses that came before. This is invaluable as we try to bring clarity to what often feels like an overwhelming amount of information. So far, we have learned how to describe the data and display it for easy reference. We have learned how to detect disease risk from specific exposures. Now we must learn how to apply statistical analyses to understand if the elevated risk is random or, in fact, a product of the exposure. Now for some vocabulary. A statistic is a single measure of some attribute of a sample, whether it's the mean or range or standard deviation, etc. A parameter is a numerical characteristic of a population. This is an important distinction. Statistics refer to our sample, while parameters refer to the population we are attempting to draw conclusions about. A hypothesis is a supposition or proposed explanation made on the basis of limited evidence as a starting point for further investigation. The hypothesis is central to any study and must be referred back to throughout the analysis process. In statistical hypothesis testing, statistical significance, or a statistically significant result, is attained when a p-value is less than the significance level, denoted alpha. If this doesn't make a lot of sense right now, hopefully it will begin to as we move through the section. The confidence interval is an interval estimate of a population parameter. In other words, when we generate statistics based on our sample, we have to consider any error associated with those statistics as we extrapolate to the population. That error produces an interval that gives us a measurable amount of confidence that the population parameter falls within it. The confidence level refers to the percentage of all possible samples that can be expected to include the true population parameter. In basic terms, this is the percentage value representing our confidence in the estimate and associated confidence interval. So let's start at the population level. Here we have our community, made up of men, women, and children of different ages and backgrounds. When we sample, we are obviously grabbing a subsection of the population. We can grab from here or here. Really, any subset of the population can be sampled. But we must be deliberate in our methodology so that the sample we draw is representative of the population. Sampling methods will be covered in the next section. For now, let's concentrate on the sample itself. What we want to do is understand what is happening within our sample and if what we are seeing is representative or significantly different than the population. So does the sample represent the population? Good question. We can look at any number of statistics or characteristics of the sample in comparison to the population. For instance, mean age or the distribution of gender within the sample. We could look at educational attainment or cancer prevalence or even self-reported mental health. All of these variables can be summarized and compared to what we know about the population in order to understand how our sample relates to the community as a whole. Focusing in on mean age, we can make a simple comparison to the population and begin to understand our sample. If we drew a sample from a particular part of the country, say your home county, we may want to know if the population in that county is significantly older or younger than the rest of the country. The U.S. mean age for 2015 was estimated at 37.5 years. Does our county sample differ significantly from that estimate? No. Saying the county is older or younger than the rest of the country in this case means the mean age in the county differs significantly from the mean age of the U.S. based on a hypothesis test using a specified confidence level. Let's say we draw a sample and we find that the mean age in our observed group is 41. The question is, does this indicate the county's mean age is higher than the U.S.? Before we can answer that question, we need to consider some measures of the characteristics of the data in our sample. We've already discussed a few, primarily those associated with central tendency, or where the data tend to cluster. We've already talked about range, which is a basic measure of dispersion or spread of the data, but in order to start drawing conclusions about the sample data as they relate to the overall population, we need to delve into more rigorous measures of dispersion, namely variance and standard deviation. Let's consider a few example distributions. The figure here displays 4 separate distributions of data represented by different color curves. These curves indicate the frequency, the vertical y-axis, of data points across a range of values, the horizontal x-axis. In other words, where the curve is higher up on the y-axis, the more data points are found near the value indicated at that area on the x-axis. Starting with the blue curve, we can see clearly that the distribution is clustered tightly around the center of the x-axis, meaning the vast majority of the data points are found very close to the mean of the sample. Comparing the green curve to the blue, we can say that the spread of the data is greater with more data points found farther away from the mean. Also, the mean is not centered on the x-axis. The beige or mustard-colored curve is really flat, indicating the data points are spread way out across the x-axis. Now the red curve is what we want for mathematical reasons. It just has the characteristics we need to conduct the tests we like. It's the Goldilocks test. Not too clustered and not too spread out, with the mean found right in the center of the x-axis. Standard deviation and variance are statistics we can use to describe the distribution of the data and conduct hypothesis tests based on these distributions. The reason we got excited about the red curve in the previous figure is because it fits the statistical criteria for the normal distribution, which is incredibly important in the vast majority of statistical analyses. Every analysis has a set of assumptions that have to be made in order to produce statistics that can be considered representative of a target population. One major assumption is that the data in our sample is normally distributed. I hope to be able to show you what that means and why it works, but first, a few disclaimers. Fact. Statistics are riddled with assumptions and subjective decisions. Fact. Without these assumptions and expert choices, none of our calculations would work. Fact. No statistical conclusion is conclusive, as every analysis has inherent error. Don't fret. This is what they call peeking behind the curtain. Understanding the error associated with every statistic presented to us in the media and professional settings makes us better consumers of information. Now on to the central limit theorem, which states, given certain conditions, the arithmetic mean of a sufficiently large number of iterates of independent random variance, each with a well-defined expected value and well-defined variance, will be approximately normally distributed, regardless of the underlying distribution. What does that mean? Essentially, if we use proper methodology to draw many samples of a large enough size, the means of these samples will be normally distributed. So now our normal distribution represents a distribution of the mean values of multiple samples. This is important because we know that unless our data are highly skewed and our sampling methodology is sound, we can assume a normal distribution, because if we were to take a bunch of samples of the same size using the same methods and plotted the means of those samples, the distribution would be normal. This means that if the mean value of a particular sample is exceptionally high or low compared to the population mean, we can draw conclusions about whether the sample mean difference represents an actual difference or is a product of the random sampling conducted. Consider our sample mean age. It could be the same as the population mean age, right in the middle, or we could have a sample with a mean age much higher than the population, or much lower. In our previous example, we had a sample mean age of 41, and the question was, does this indicate the county's mean age is higher than the U.S.? We need a little more information before we can answer that. Let's talk about confidence limits. Before we can conduct our comparison analysis, we have to decide how confident we want to be in our conclusions. What do you think? Do you like to be 80% confident in your statements? 90%? 100%? It probably depends on what you're talking about, right? The same is true in statistics. Analysts decide what the cutoff is for the probability of being wrong, and if their calculations fall under that cutoff, then they feel good about their conclusions. Does that seem funny? We decide the criteria for being right. The reason we are able to do this is because we state clearly what our confidence limit is and usually rely on previous work to inform our selection of that limit. Still, this is important to understand that there is always a subjective element in statistical analyses. Let's look at how to build a confidence interval. First, in review, every statistic is an estimate, with error based on the nature of the data, i.e., standard deviation and sample size, as well as the confidence level selected for the analysis. So here is the formula for calculating the confidence interval for estimating the mean of a population. Looking at the specific elements of the formula, X bar, as it is called, is the sample mean. T is associated with a standardized statistic that we'll cover in a moment. S is the sample standard deviation calculated using the formula here. And N is the sample size. What the formula is saying is the mean estimate has error that is increased by larger standard deviation but can be reduced by drawing a larger sample. T times the standard deviation divided by the square root of the sample size n is the error of the estimate. Thinking of fractions, if we increase the sample size, the error goes down. If we increase the standard deviation, a measure of the spread of the data, the error goes up. Stopping on standard deviation for a minute, let's try and visualize this measure. Our data points have space between them that is meaningful if the value is numeric, right? For instance, the age variable. Each individual in our sample is going to have an age associated with them, and we want to be able to understand how much standard space is between each individual's age data point. The way this is represented mathematically is the average distance from the mean for each data point. Square rooted, this is the standard deviation. Quick side note, we are not estimating the mean of the sample. That is empirically observed. We are estimating the mean of the population based on the sample characteristics, the mean, standard deviation, sample size, etc., also using the chosen confidence level. So back to our visualization exercise. We have 5 individuals, all with different ages. To calculate the sample standard deviation, we use the formula here, which is essentially the square root of the average difference between each data point and the mean. Why that math works isn't important for our purposes here. To restate this one more time, the size of the standard deviation is a function of the average of differences between the sample mean and every other value in the sample data set. For example, here that difference is age diff. Therefore, the spread of the data points, age, in our sample impacts the size of the standard deviation and thus the error in the population estimate and thus the size of the confidence interval. So if we tighten the distance between data points and assume the same sample size n, the standard deviation for this sample would be smaller, making the error in the population estimate smaller. This makes intuitive sense if we look at the sample visually as it is displayed here. The data points are clearly clustered more than in the previous sample, suggesting the population age does not vary as much, making it easier to estimate the mean, i.e., less error. Back to our formula for building the confidence interval for estimating the mean of the population. We've covered the elements associated with standard deviation. Now let's look at T. T is the student's t-test statistic, named after a fellow back in history with the last name Student. We use t-values to standardize our calculations so that units of measurement do not affect the error estimate. We select the t-value for our confidence interval calculation based on our chosen confidence level. Observe. The one thing we must have is what's referred to as a t-table. You can Google one anytime so they are readily available. The t-value selected using the criteria I will discuss is essential to the process of building a confidence interval. The majority of statistical analyses are conducted using a 95% confidence level. This is just based on convention. It means that the mean confidence interval produced from a sample will contain the actual population mean 95% of the time. Remember the central limit theorem? If we take 100 samples, we would expect that 95 of those sample means will fall within the range of our interval. Of course, this leaves us with a 5% chance that the actual population mean falls outside of our interval, and therefore our estimate is wrong. If you look at the table to the right, you'll notice several things. 1. There's a normal curve pictured at the top of the page with a shaded area labeled probability P. This shaded area represents the extraordinary values in the distribution, those that likely occur 2.5, 5, or 10% of the time depending on our selected confidence level. 2. Across the top of the table, there are values listed for the probability P area of the curve. 3. There are a series of sequential numbers down the left-hand column under the heading DF. These are the degrees of freedom, which simply put are calculated for basic confidence intervals by subtracting 1 from the sample size, i.e. n minus 1. So, we decide on our confidence level, typically 95%, and use our sample size to find a t-distribution critical value which corresponds to the point on the distribution separating ordinary values, or those occurring 95% of the time, from the extraordinary values, or those occurring 5% of the time. Let's go through an example because I know that was a lot to hold on to and digest. Once again, here's our confidence interval formula. In the age example, we will assume a sample mean of 41, standard deviation of 3. The sample size is 30, so using the n-1 calculation, we know that our degrees of freedom is 29. And we will use the common 95% confidence level. So if we start plugging numbers in, we can get this thing calculated. First we plug our sample mean in the formula. Now the next thing in the order is the t-value. So what we do is reference our degrees of freedom, 29, finding it on the table. Then we find at the bottom of the table our confidence level, which is 95%. Then we find where the DF row meets the confidence level column. And it looks like the number found where they meet is 2.045. Let's plug it in. Now we just plug and play, putting in our sample standard deviation and sample size. Run the math and we end up with 41 plus or minus 1.12, which generates a confidence interval of 39.88 to 42.12. This means we are 95% confident that the population mean age is between 39.88 and 42.12 based on our sample. We expect that if we draw many samples, that 95% of the sample means will fall between 39.88 and 42.12. Assuming we've not made errors in our sampling methods or calculations, there is only a 5% chance that we are wrong. Now let's go all the way back to our original question. Does the county mean age differ significantly from the U.S. mean age? Really what we want to know is the sample mean extraordinary. That is, it is highly unlikely that it is found due to randomness, that it significantly differs based on our analysis. On this topic of extraordinary values, let's talk a second about the distribution of data within the normal curve. We can parse out sections of the curve by considering standard deviations. It is assumed that 68.27% of the population is within one standard deviation from the mean, and that 94.45% of the population is within two standard deviations. This leaves about 5% split between the two tails of the curve. You can see then that values lying outside of two standard deviations from the mean are uncommon and can be considered extraordinary. Let's try and bring it all together. If we know our sample standard deviation, then we can make a judgment about the distance between the population mean that our sample mean lies and whether that is extraordinary. One more example. Let's consider the mean number of minutes it takes for high school students to complete a standardized test. We may want to ask if a particular racial group is taking longer to complete the exam on average. This can occur due to cultural differences between groups of students. For example, this is what we know. Population mean is 39 minutes. Study group mean is 47 minutes. Population standard deviation is 3, and we're selecting a confidence level of 95%. So, one standard deviation is 3 minutes. So 39 plus one standard deviation is 42. 39 plus two standard deviations is 45. But we need to calculate the lower limit as well. 39 minus 2 standard deviations is 33. Therefore, 95% of the population completes the exam between 33 and 42 minutes, meaning the racial group is taking significantly longer, 47 minutes, on average to complete the exam, as that group's mean completion time is greater than 2 standard deviations from the population mean of 39, meaning there's only a 5% chance that we have selected a sample that is randomly outside of the population mean confidence interval. To clarify, obviously racial characteristics are not causing students to take longer to complete an exam on average. This is an example of a hypothesis generating result. As good social science researchers, we then would need to explore factors common to the racial group, for example, socioeconomic status, cultural norms, parental education attainment, etc. Good sampling methodology and exploratory analysis can help us better understand the support needs of specific communities and subpopulations. Looking ahead, all of this mess starts with a review of the available data and research. There's never enough money available to support public agencies conducting redundant research. Exploration of the available data should either answer all of our questions or guide us toward the questions needed to move forward in supporting a healthy and vibrant community. Once we have a question in mind, we then need to carefully select samples of the population using sound ethical and scientific practices. Being able to extrapolate our findings to the target population relies heavily on the way we draw and manage our samples. Now we're going to take a short break so you can assess your grasp of the information presented. Once you've finished the assessment, you can start with the next section of the module.